For section 5.4, which is what we're going to cover in this second part, you will need that formula sheet for test 3. So you can pull it up and have it on your device, or hopefully you already have a printout. So 5.4 is called the central limit theorem. And if you pull up your formula sheet, it's going to take me a second to do that. I'm going to pull it up on my laptop so I can see it correctly. Okay, I'm there. And you'll notice that number 2 has several parts. So this is the test 3 formula sheet. And all of number 2 go with section 5.4. And I just realized you can't see what I'm writing, so sorry about that. So on the test 3 formula sheet, all of number 2 go with section 5.4. The questions from 5.4 will be towards the end of the test. And so just know that, so the only formula you're going to use on that formula sheet, except for the last questions, is number 1, that changes a z-score to a data value. Then number 2, you'll see some different things about, there's an A, and this says the mean. I'm going to go ahead and write what's on the formula sheet for you, and then I'll show you how to use it. The mean of, I'm going to abbreviate this, a sampling distribution of the sample means. Actually, I can't abbreviate that much. The sample means. That's what the A part is. And I'm going to do these, I'm going to write the formulas as we use them. The B part is the variance of this. The C part gives you the standard deviation. And the D part talks about the z-score. And I think that's it. Yeah. So what that means is we're going to have special formulas when we're doing a sampling distribution of the sample mean. So what does that mean? That's what I'm going to show you. So a sampling distribution of the sample means. And let me get and this is kind of light, so I'm going to use a different color. The sampling distribution of the sample means. Here's what the situation is for that. This is what that means. Let's suppose you were interested in what the average age was for TCC students on South Campus. Let's pretend we're on campus, okay? So you were interested in the average age of all of the students on South Campus, but you didn't want to ask all like 5,000 of them their age, or you didn't want to look at 5,000 ages. So instead, what you did was you took some samples, okay? So you took several samples. Let's say you just took 5 samples, okay? And let's say your sample size, so we're going to take some samples of size. Remember, sample size is little n. And let's say we take a sample size of n equals 30. So your sample size is significant and important. 30 is like a magical number, so that if your sample size is at least 30, you get better data. If your sample size is less than 30, then your data isn't so meaningful. So let's say you take some samples. Let's just say we take 5 samples of 30 people. So 150 people total instead of 5,000. So let's say here's our 5 samples. 1, 2, 3, 4, 5. And each of these samples has 30 randomly selected students in it. And so we go to this sample 1 here. So this is our sampling distribution. So we go to this first sample and we find the average age of those 30 people. Remember, there's 30 people in each sample. And on these people, that's a sample. So it's going to have a sample mean, and we're going to call it sample mean. We'll just call it sample mean 1. Then we have another 30 randomly selected students, and we're going to call the average age in that sample X bar 2, meaning the sample mean of the second sample, and so forth. So then we'll have a sample mean for these 30 randomly selected students, and these would be non-overlapping samples, and then a 4th one, and then a 5th one. Now you see what I have now are 5 sample means. It's not important how many samples you take. In this case, we took 5 sample means. But those 5 sample means would be called a sampling distribution of sample means. So now think of those as 5 numbers. And we're going to take those 5 numbers and treat them as if they're our data. And we're going to find the mean of the sample means. I know that sounds kind of weird. So the mean of the sample means, that means we're going to take the average of these 5 numbers. Now we got those by taking these averages up here that had more people in them. But now we reduce that to 5 sample means. And when we have a sampling distribution of sample means, something magical happens. The mean of those sample means, when you average those sample means, and they're going to call that mu sub x bar, the mean of the sample means. And if you look, that's going to be the A formula here. The mean of the sample means, and you'll notice that, look at part A. The mean of the sample means, look, notice it says equals mu. Now, what that means is that by averaging those 5 sample means, I will get the mean of the whole population. Remember, there were like 5,000 people in the population? We took 5 samples of 30. We got those means. Then when we average those averages, sounds kind of weird, so we would add them and divide by 5 because there's 5 of them. So we would take like x bar 1 plus x bar 2 plus x bar 3 plus x bar 4 plus x bar 5. We would take the sum of those and divide by 5. That would give us the mean of those sample means, and it would be equal to the mean of the population. If, okay, look back at the top of the formula sheet, it says central limit theorem. And this works if, I'll write the if here. If n is greater than or equal to 30, so your sample size has to be greater than or equal to 30. Remember I told you 30 was a magic number? Or the original population like the ages of the whole 5,000, is known to be normally distributed, or the population is normally distributed. And I don't have room to write that whole word, so I'll just put DIST. So this will be true if the sample size is greater than or equal to 30. That's why I picked a sample size of 30. The bigger it is, the better. But what it's saying is I can take these 5 sample means and average them, and that will be equal to the mean of the whole population. Now, so the mean of the sample means is the same as mu, is the mean of the population. The variance standard deviation, though, are different. So if you look at your formula sheet, we are given formulas for the variance. So I'm going to write these down, and then we're going to work some problems. The problems are easier than what you would think. So the variance of the sample means, this is the B part. The variance of the sample means is going to be the variance of the population divided by the sample size. So that's a second formula. Then the C part, the standard deviation, and I'm going to erase this and we'll talk about this in a minute, okay? So this first one, we have that one. And we have to remember that n has to be 30, or the population has to be known to be normally distributed. But even if the population is not known to be distributed, then that just means you need a sample size of at least 30 for these things to hold true. So we had this here, the mean of the sample means is the same as mu. The variance of the sample means is the variance of the population divided by n. The standard deviation, that's sigma, of the sample means is just the square root of this. So if you look at your formula, it says it's going to have, when you take the square root of this, you get sigma over the square root of n. And that's basically just taking the square root of this number here. And then to find the z-score, this isn't really a new formula. It's just that when you're doing the z-score, you have to take, you're doing a z-score for a sample mean. You have to subtract the mean of the sample means, which is the same thing as mu. Remember, the mean of the sample means is mu. And you have to divide by the standard deviation of the sample means. So you have to divide by sigma over square root of n. So your z-score formula looks a little different because you have to use the mean of the sample means, mainly because you have to use the standard deviation of the sample means, which instead of just being sigma, is sigma over square root of n. Now I'm going to go to a few problems in my stat lab to show you how we're going to apply these formulas. So, and my computer just went kind of bonkers here, so hopefully I can get back in. So I'm going to the 5.4 homework in my stat lab. We're going to look at the first few questions. We'll do as many as we have time for. 5.4. And let's just start with number 1. And I'll just leave these formulas up here and refer to them to show you how we're going to refer to our formula sheet. So this is basically, I've written the formula sheet up here on the board. And then over here, we'll do some examples. And we'll just start with number 1 from the homework. Number 1 says, let's write, it has some given information. So remember we talked about doing what are you given, what are you supposed to find? You might write that down every time you work a problem. What have they given you, and what do they want you to find? On this one, we're given that a population has mean of 169 and a standard deviation of 27. And it says, find the mean and standard deviation of the sampling distribution of the sample means. So let me show you how to represent that. They want the mean and the standard deviation of the sampling distribution of sample means. So what they want you to find is the mean of the sample means and the standard deviation of the sample means. So I put the little X bar that tells me I'm looking for the mean standard deviation of the sample means. Now they did give me one other piece of information. It says the sample size is 44. So I'm going to write that down. I'm going to write that down. That's something that's given. The sample size is 44. And now I'm going to try to find the answers. So the first thing they ask for is the mean of the sample means. So that's this first part. We'll come back over to our formula sheet. The mean of a sampling distribution of sample means, notice it says the mean of the sample means is the same, is equal to mu. So the mean of the sample means must be 169. So I'm going to put that in as my answer for the mean, 169. And so that's the first part. And then the second part is the standard deviation of the sample means. Remember what this means is we took a bunch of sample means and we're treating the sample means as if there are data. The average of those averages, the average of those means is saying will be the same as the average of the population. And the standard deviation, look back over here, our formula for standard deviation is sigma over square root of n. That's how we get the standard deviation. So on this one, our sigma is 27 over the square root of n is 44. You may remember we had some problems like this in our basic skills review. This is why we were doing those, to make sure we can find these answers. And they want us to round this to 3 decimal places. So we worked on doing this sort of thing in our calculator back at the beginning of the chapter. Now we're going to use that. So I'm going to do 27 and divide by the square root of 44. And I get 4.0704. And they tell me to round that to 3 places. So that means I needed to know that fourth number. So to 3 places, the standard deviation of that sampling distribution of the sample means is going to be 4.070. And there's the standard deviation, which notice is different than the standard deviation of the population. The standard deviation of the means will be always smaller than the standard deviation of the population because the means are more condensed, so they're not spread out as much. Remember, standard deviation is a measure of how spread out the numbers are. So the population numbers might be really spread out, like when we're talking about ages. So the ages of all the students on South Campus, they may range from like, I don't know, 13 or 14 to 90 or more, okay? So the standard deviation is going to be pretty big. But if I take a bunch of samples of 30 or more, and I average the ages in those samples, the average age in each of those samples is not going to be that wide. The average ages are going to be in a much narrower, those means are going to be a much narrower range of values, which means the spread will be less and the standard deviation of the means will be much smaller than the standard deviation of the population because the numbers aren't nearly as spread out. So on this one, I'm going to put in the answer just to make sure we're right. 4.070. Okay, so that's correct. And let's go to a different question. See if I can find one that's Okay, here's a good one. Number 5. Let's do number 5. And I think I'm going to condense this a little bit. I'm going to put the parts that you need most are the A and the C parts. So the A part told us the mean of the sample means is the same as the mean of the population. And the C part told us standard deviation of the sample means is the standard deviation divided by square root of n. So those are the 2 main formulas I'm going to need. I'm going to put just those 2 up here. And let's go to number 5. See how much time we have. Okay, so number 5. And it says, the population mean, let's write down what are we given, what are we supposed to find. Get in the habit of doing that every time. So this one says, it says the population mean and standard deviation are given. Find the required probability and determine whether the given sample mean would be considered unusual. So here's what I'm given. This is the information I'm given on this. It says for sample size 70, so my sample sizes are 70. It says find the probability, so I'm putting this under find because it says find. Find the probability of a sample mean, so X bar, being less than 19.6 if, and then they give me some more information. They tell me that mu is 20 and my sigma is 1.17. We are also going to need the D part. We're going to need this D part as well. Notice I put parentheses around this denominator here. That's because that's how I'm going to enter it in the calculator. So I'm looking for this probability. Now what I know is that these sample means are normally distributed if one of 2 things happens. The sample means will be normally distributed if the sample size is at least 30. Notice my sample size is 70. Okay? Or if the population is normally distributed. So they usually tell you one of those 2 things. So the population, if the population is not normally distributed or if it's not known, then you need a sample size of 30 or we've got that. That means because of that sample size, our sample means will be normally distributed. Now, the significance of that is that if the sample means are normally distributed, that we can use the normal distribution table, you know, our handy dandy little table to calculate probabilities. But we don't calculate probabilities about data values or means. We calculate probabilities. We have to use the table. We can only find those probabilities if we know the z-score. So the first thing we need to do is we're going to have to change that probability to be about a z-score. But to do that, to do the z-score, I'm going to need to figure out, I need these numbers. Okay? Now realize that this thing down here, that's actually the standard deviation of the sample means. Now I could come over here and I could say, okay, based on this here, I know the screen is not very dark. I don't like it. Based on this information, I know that the mean of the sample means is 20. The standard deviation of the sample means, if they had asked me that, is going to be sigma. It's this right here. This is the standard deviation of the sample means. The sigma over the square root of n. Now, if you do this calculation here, don't round it too much, like take it out a bunch of places. So I'm going to do that here. I'm going to take it out 1, 2, 3. I took it out 5 places. That should be okay. So what I just found was the mean and the standard deviation for the sample means, because I'm doing a probability about a sample mean. Now, what I want to do with that probability of the sample mean is I want to change it to a probability about a z-score for that sample mean. I'm going to put a little x bar on that. So I know I'm looking for the z-score of a sample mean, and I need to find the z-score of that sample mean. That's where this comes in, right here. So to find the z-score of the sample mean, I'm going to do the data value. This is what you're going to use for x right here. So I'm going to have 1.96 minus mu. The mu for the population and the sample means is 20. Oh, I'm sorry, it's 19.6. Sorry. I put the decimal in the wrong place. That's going to make a big difference. 19.6 minus 20 divided by, and you could put this whole thing here, but we just found this. We just found the standard deviation of the sample means right here. We did sigma over square root of n. So we've done that. We already know it's 0.13984, and I don't want to round that because I don't want it to throw off this z-score. So I'm going to do 19.6 minus 20. This is going to come out negative. And I'm going to divide by, and I could do this one of 2 ways. I already figured out this over here. So I'm just going to divide by that number I got. But I could also just do parentheses and put those numbers in. So you can do it all in your calculator. Or you can, if you find this separately, this sigma, like I did over here, make sure you don't round it, because that will throw your z-score off, and then you'll get the wrong answer. So I think taking it out, we'll see if taking it out 5 places works. And that gave me negative 2.86. That's what I get for the z-score. So over here, I'm looking for the probability that a z-score is less than negative 2.86. At this point, guys, this is exactly like our probability questions that we had before. Identical. So you're going to draw a picture with z-scores. Here's 0. Negative 2.86 is over here. Since this is a less than problem, less than, that means to the left. So I'm looking for this area here to the left of negative 2.86, but I know how to find that because this table, now that I know that these sample means are normally distributed, I get to use the normal distribution table. So I'm looking for this area to the left of negative 2.86. Negative 2.86 is 0.0021. And because I'm looking for the less than probability, that area to the left is the probability. So this equals 0.0021. And that's which is a very tiny probability. A very tiny probability that a sample mean, a randomly selected sample, will have a mean less than 19.6. That's what we're talking about here. You're finding probabilities about sample means. So I'm going to put my answer in here. I got 0.0021. Okay, and it says, do you think that's unusual? Well, remember, unusual means less than 5%. This is definitely less than 5%. So I'm going to say the sample mean would be considered unusual because as a probability that is less than 5%. And that's all of question 5. So let's write this is unusual because it's less than 0.05. So we have sort of an extra step in here, a different formula for the z-score. But once you have that z-score, the problem is identical to what we were doing in section 5.2. Identical. The only difference is we have to use a slightly different formula for z-score when we're talking about the distribution of the sample means instead of the distribution of all the data. Okay, so my time is up, and hopefully you can get through most of your homework, but over the weekend, please use your weekend. I want you to be ready for the test. Monday is a review. The test is going to start next Wednesday, test 3. It's only over chapter 5. Do not put off your homework until Monday. I'm telling you, that's a bad idea. You've got to give your brain time to think about it and practice on it. And practice showing your work, practice showing your work in my stat lab, practice writing the given and define like I've shown you here, practice drawing a picture for pretty much every problem. And you guys have a great weekend. I will see you on Monday, and hopefully you can get through all of chapter 5. Bring your questions to me on Monday. Okay? Have a great weekend.